Okay, so I think we were just starting on this one. Let's look at a couple more of these, then you can decide how much of this you want to go through. But about the first half of these problems, first 6 or 7 were ones that a substantial number of people seem to be having troubles with. Okay, so this one we said we gotta rewrite this function so we can see all 3 layers and we can see how to apply the chain rule. Now we just have to do the chain rule. So what's the first layer in the first link in the chain? Squared. So I've got something squared, derivative of something squared to something to the 1, right? Something cosine. Next layer. Yeah. So derivative of cosine in hand is negative sine. We done? One more. Times 7 pi. Yeah, t is the variable, right? And so 7 pi is the coefficient. So there's our derivative. Not a whole lot we can do to clean that up. We could pull the minus and the 7 pi and the 2 all out front and get what? Negative 14 pi. And then we've just got a sine of the angle, whoops, and a cosine of the angle. There is one trig identity that we could use here if we really wanted to. Let's see if they did. Nope, they didn't. So that's it. Okay. Fair enough. Questions on that? Okay. All right. So something different. How about? Oh, nothing there. All right, so this doesn't seem like that big a deal to me. You guys want to do this one or not? Yeah. Okay. So, so this one, I bet you the problem on this one is coming from the fact that you've got a product rule and the chain rule, right? So, what's the first thing we have to do to this? You always got to look at the function kind of from the outside, looking in from the outside. What's the pattern? Is it power? What's the first thing we have to view this as? Power, product, what do we have to do? It's product. Yeah, it's product of 2 things, right? Now let's what are those 2 things? Well, we have that thing, the x cubed, that factor, and then we have this factor right there, the quantity 2x minus 5 and 4. Those 2 things are being multiplied. So it's a chain rule before anything else. I mean, excuse me, a product rule, not a chain rule. Do we want to, maybe the question comes up, do we want to expand this thing out first and then distribute the x cubed and make it a polynomial? Probably not. That's a pretty big expansion right there. 4th power. Definitely, I'd say not worth doing. Okay, so we got to treat it as a product. What's our product rule tell us then? Okay, good. So we got the first function times the derivative of the second, or it doesn't matter which order you do this in for product rule, right? You're adding the 2 terms anyway. Now, what's the derivative of this guy going to look like? Okay, good. I've got that. That's a chain rule issue, isn't it? I've got a power, and then inside the power, I've got something else I can also differentiate. But at the outside, the blue factor is a power. So 4 times the quantity cubed, right? And then what's the derivative of 2x minus 5? 2. Okay. plus 2x minus 5 to the fourth times the red derivative. What's the derivative of x cubed? 3x squared. All right. So we're done with the calculus. That's it. Now it's just a matter of cleaning that up, a little algebra. So we want to factor stuff out. Now, something that you've probably noticed here, when we're taking a product of powers like this, now think about what we just did there. Just kind of step back from the actual nitty-gritty and just kind of think about this conceptually. If I'm going to take one factor times the derivative of the other plus the other times the derivative of the first, when I'm differentiating those powers, the power rule always drops the powers by 1, doesn't it? Right? So doesn't it make sense that that both of those bases then are going to show up in each part, but in each part, one of the exponents has been dropped by 1, right? Make sense? So I'm going to be able to factor out those like bases, right? And in the first term, the first part of our product rule here, we left the x cubed alone. So I'm going to end up with x's left over there because the x's are going to be reduced over there, aren't they? Right? In the other one, we left the quantity 2x minus 5 alone. So in the first derivative, that had to have been reduced. So we're going to have that base kind of left over when we factor stuff out in the second term because this one's been reduced. See where I'm going with that? Okay? So it's sort of predictable how this is going to work. So then we can pull out maybe some constants too. Well, maybe not. I have 3 here and just a 2. Okay, so the numbers, can't take any numbers out, can we? But what about the x cubes? What's the biggest common power of x? Of x's? X squared. Okay, I can take an x squared away here, and I've got still 1 left over here. So let's factor out an x squared. What else? How about this other base, 2x minus 5? Okay, good. We can take the other base cubed. And then that leaves me that from the first term, the x minus 5 to the third goes away. We factored that out completely. We take all but 1 of the x's away, right? And then it looks like we're just left with 8. Oops. 8x, right? What about the other guy? Plus. We can cancel the x squared out completely, right? And we're going to take all but 1 of the 2x minus 5's. So then we're just left with 3 times the quantity 2x minus 5. Okay, so what's the last thing I probably can do here? Yeah, I could combine all this stuff. I can distribute the 3 and add like terms. And so we end up with x squared times the quantity 2x minus 5 cubed times, what am I going to get? How many x's? 14 looks like. 14x. Minus 15, good. And that should do it. Yeah, okay. That's it? Okay. Second derivative. This one was a problem a little bit. I want to talk about this one. Okay, I may I may go in and edit this problem a little bit so that it changes how it grades it. But I don't know. We'll see. We'll talk about it. Tell me what you think after we're done. So if y equals 2 cosecant x, and I want to take a second derivative. First of all, what's the second derivative mean? The double hashes there. Double primes. Derivative of the derivative. Okay, good. So first we need a first derivative. So what's y prime going to be? What's the derivative of cosecant? Good. Negative cosecant cotangent. So we end up with negative 2 cosecant x cotangent x. And that looks an awful lot like what? Product. Yeah, got a product of things. And that negative 2, I might as well just pull that out front. Okay. I'll just do that. I'll just focus on the product of the cosecant and the cotangent. Leave the negative 2 out there. So, talk about that product. What's that going to look like? What's the derivative of cosecant cotangent? This product, right? We've got 1 times the derivative of the other. What's the derivative of cotangent? Negative what? Cosecant squared. Okay. Yeah, remember this is, if you know tangent, you know cotangent. Derivative of tangent is secant squared, so the derivative of cotangent must be negative cosecant squared plus cotangent x times the derivative of cosecant. What's that? Yeah. Cosecant x, negative cosecant x, cotangent x. Right? And I could expand these out, right? Multiply these out. What do I get? Negative 2 times negative. Let's go ahead and distribute the negative 2 while we're at it also. So we're going to get positive 2 cosecant cubed x minus, no, plus, yeah, plus 2 cotangent squared x cosecant x. Okay, that seems like that, to me that should be probably fine, but it's not. They want you to go a little further with this. Now, I want to show you something here. It's kind of cool. If you know the Pythagorean trig identity, you actually get a 3-for-1 deal on this. Okay, so we know that sine squared x plus cosine squared x equals what? 1. Okay? So now watch what happens here. If I want to write this thing in terms of the other functions, the other trig functions, I'm either going to divide everything by sine squared or everything by cosine squared. And watch what happens when we do both. If I divide everything by cosine squared on both sides, what do I get on the left? Yeah, I'm going to get tangent squared plus 1 equals secant squared. Okay, so there's a second Pythagorean trig identity. Now let's do the same thing over here, but let's divide by sine squared. What's that going to give me? Plus cotangent squared x equals okay, so we got 3 for the price of 1. So now can we use that stuff and simplify further our answer? In other words, could we write this, and what might be our motivation for this? You're probably sitting there thinking, well, what's this really doing? The advantage of this is, and this is something that we will deal with later, we'd rather have one cross-contamination going on here when we have cotangents and cosecants. Because usually our goal is to take a derivative or a second derivative and then find the zeros of that. And so when I set this thing equal to 0, I'm going to be trying to factor, right? It's a lot easier to factor stuff if I'm factoring in terms of a single type of trig function than multiple types of trig functions. So that's really behind the scenes. There is some motivation for this. So is there a way then, it looks like I've got cosecants here, and I've got a cotangent in the second term also. I guess what I'm asking is, could I trade that cotangent for some cosecant stuff instead, so I'd have only cosecants?
Cosecant squared minus 1.
Yeah, I could say this cotangent squared x is right there, right? Cotangent squared x would just equal cosecant squared x minus that 1. We'll push it over the other side, right? Good. So let's make that trade. So this guy, whoops, this guy becomes the quantity cosecant squared x minus 1. Everything else stays the same. Okay. So now if I distribute the 2, what's going to happen? Looks like I get plus 2. Let's go ahead and distribute the 2 cosecant x. So I'm going to get plus 2 cosecant cubed x, right, minus 2 cosecant x. Do we agree? So then these combine to become 4 cosecant cubed x minus 2 cosecant x, and I'm pretty sure that's how they're wanting this. Yeah. Okay. Okay. Oh, yeah, cut the x off. Whoops. Well, I was cutting and pasting. So maybe how about this? I'll reword this one, because that seemed a little unclear. I'll reword this one to say, express the answer in terms of a single trig function or something like that, or cosecant x or something. So it reminds you to do that. Okay. Yep. Let's go back down. Yeah. And I'll tell you what, if you want to have, I would have no problem if you want to have a list of the trig identities there, that's fine. In fact, I will, is that one on the website, on the Moodle site? If not, I'll put it on there today, like right after this class, I'll put it on there. So then if you want us to open that up, open up the Moodle site, a separate window, and have that one available or something, that's fine. Or print it out, I don't care. Okay? Okay, we good? Okay, and then I want to get to a couple of these kinematics ones. So here we have position function, s of t equals negative t cubed plus 12t squared minus 45t, right? And we want to find the body's acceleration each time the velocity is 0. Okay, so before you start jumping into this, really take a second and think about this. Now, what's this asking us to do? Let's kind of wrap our brains around this. So we're going to find, how do we find velocity? Okay, differentiate with respect to t. And then acceleration. Okay, take the derivative again, right? So that's no big deal. That's polynomial. That'll be easy for us. Find the body's acceleration each time the velocity is 0. So what do we do to find each time the velocity is 0? Set equal to 0 and solve. Solve for those values of t. And this is a graphing calculator test, so however you want to, and use, whatever you want to use. You can use you graph it. You can use polysmolt or the other one you guys always use, backward out. I don't care. Whatever you want to do. And then I'm just going to feed those values of t into the acceleration function that we did, right? That's pretty straightforward. So V then, V of t is going to be what? Okay, and while we're at it, let's go ahead and calculate acceleration. Okay, so then if we just do this, if we just set this guy equal to, whoops, terrible color. Set that equal to 0, I bet that's even a factor, isn't it? I can take a negative 3 out of everything, and I'm going to get, what, t squared minus 8t plus 15 equals 0, so negative 3, negative 5. So t minus 3 times t minus 5 equals 0. So what are my two values of t then? 3 and 5. So I'll just plug those in into A. A of 3 is going to be 6, negative 18 plus 24, right? A of 5 is going to be negative 6. So we got it. 6 and negative 6. Okay. All right, now you just tell me which ones you want to do from here on out. Give me a yay or an A on this. Find an equation for the line perpendicular to the tangent to the curve. Yay or nay? Any takers? Any takers? Do it. Do it? Here? Okay. So we want an equation for a line perpendicular to the tangent. I want an equation for a line, so what are the ingredients? What do I need to write the equation of a line? Slope and a point. Good. Got a point. That's a freebie. Just need a slope. How am I going to find the slope? Derivative. Okay, so y prime equals what? 3x squared minus 9. Okay. So how do I find? Okay, good. Plug the x and y, and then plug the x in. Right. Sorry, there's no y in our derivative. We're getting to that soon, though. On Tuesday, we'll get to that. So I plug the 3 in, and I get y prime equals 3 times 9 is 27 minus 9, 18. At x equals 3. Now that's the tangent, though, right? We want the line perpendicular to the tangent. So what do I know about perpendicular slopes? Opposite reciprocals. Yeah. So the slope of the perpendicular, really what we'd say the normal in that. It's either tangent or it's normal. So that's going to give me what, negative 1/18? So there's our slope. There's our point. Just a matter of plugging and chugging. So y equals mx plus b. If I plug in m and x and y, 4 equals negative 1/18 times 3. So what's that going to give me? 4 and a 6? Is that right? 4 and a 6? So that's 25/6. That's our answer. And I don't remember, I cut off what the instructions were, how we're supposed to write it. But, oh, we want the whole line though, don't we? Whoops. So there's B. So then if we plug all that stuff back in, doesn't that make sense? M is negative 18, and there's our B, 25/16, or 25/6. Okay. Find the horizontal tangents of the curve. Yay or nay? Seeing some yays? Okay. So horizontal tangents, so y prime equals, at least we'll get to a point where we can say this is how we finish. 3x squared minus 8x plus 4 is our derivative. Polynomials are a piece of escape, right? We love those. Taking derivatives of polynomials is very quick and easy. And then what do I do if I want to find horizontal tangents? What kind of a slope is a horizontal tangent? 0. Aha. So if I want to find all the horizontal tangents, and I think what it's really asking, yeah, values of x. Just set that equal to 0 and solve. Right? And that one's not going to factor easily, at least, so that's when you'd want to put in your calculator. Right?
And then what should be like a table?
You could do, yeah, that's fine. You could do that. Well, this one, you just want the x values, and so all you're looking for is a solution to that. So you wouldn't even have to do any table stuff there. It's just a matter of choosing your preferred weapon there, and whatever kind of calculator trickery you want to use. I don't care. It'd be easy to graph this too, right? I mean, you could just graph y1 equals this, and look for the x-intercepts, the zeros. That's the other way you can do it. Everybody's got some kind of a fancy program they like, though. Does anybody, if anybody wants to get, who has that poly smolp 2? Anybody not have it that wants it? Okay. If you do, it's easy. I mean, I can just throw some chords out there and you can give it to each other. How about this one? Simple harmonic motion, yay or nay? Yay, okay. So here's our position function. And by the way, the reason this is simple harmonic motion, because it's repetitive, right? S equals 9 minus 5 sine t. Because sine t just oscillates forever, we call that harmonic oscillation in physics, or something just goes, it's just wiggling back and forth. It's got that kind of constant, like think of a pendulum, or think of a, if you hang an object from a perfect spring so it just bobs up and down forever. It's a frictionless perfect spring that has no energy loss. It goes forever like that. Now, in reality, we typically have is damped harmonic motion, where it wiggles, but then eventually, friction brings it to rest, and so it's damped down to 0 eventually. But we won't mess with that now. That's a different class. Okay, so find the velocity. Here's position. So find the velocity of the body at t equals pi thirds. Okay? What do I do? Derivative. Yeah. So v would be what? Yeah, good. Negative 5 derivative sine is cosine. So v of pi thirds is just negative 5 cosine of pi thirds. Now, cosine of pi thirds, let's just look at the unit circle real quick. Right, so if I look at a unit circle, where's pi thirds? If I break the first quadrant up into the important 3 angles that we always talk about, right, I've got, it's at 60, isn't it? Right, this is pi thirds. So what are the coordinates of pi thirds? And there's an easy way. How much did we? Well, I can't remember if we talked about this or not. There's a really easy way to remember all these coordinates. You know that if I look at all 3 of these interior angles in the first quadrant, the x and y coordinates are just different amalgamations of 1/2 square root of 2 over 2 and square root of 3 over 2, right? Well, here's how you can kind of remember this real easily without having to put too much thought into it. You know that the extremes always go together because square root of 2 over 2 is in the middle. Right? 1/2 is less than that, square root of 3 over 2 is bigger than that. That's easy to check. So the extremes always go together, and the middle value always goes with itself, right? And so therefore you know that if you're looking at the coordinates of these 3 angles, you know that this one has to be square root of 2 over 2. And square root of 2 over 2. Because it's in the middle, and the middle values go together, the extremes go together. So if we look at this guy down here, it's going to have 2 extremes, and this guy up here is going to have 2 extremes, right? But is the x value or the y value going to be bigger than normal here? At at this point. X value, right? It's scooted further in the x direction. So you know that's a square root of 3 over 2, so the y value must be reduced. Up here, the x value is smaller. And maybe you didn't even need to remember that, but that's an easy way to remember it all. And then if you know the first quadrant, you know them all, right? Because look, this one maps to that one, this one maps to that one, this one maps to that one. Only here, the x values are negative, right? Make sense? Okay, y coordinates would be positive. And then I can do the same thing right there. Right? They always, if I know these, I know all of them on the inner circle for free. Okay? So, cosine of pi thirds is, cosine is x or y? X. Cosine c before s, x before y. Right? So, the x component at pi thirds at 60 degrees is what? Right? At 60 degrees, that's going to be the one up here where x is small, y is big. Right? So, 1/2. There you go. So we get -5/2. Okay, the speed of the body. Now, okay, what about this? We got to talk about this just a little bit. I mentioned this, but we didn't spend a lot of time on it. I don't think it's really in our textbook very much. So, how is speed related to velocity? Good. Speed is always positive. You have a speedometer in your car. It's never going to read a negative value. It'd be inconvenient to have a velocitometer in your car. Because if you were going to Portland, it would register maybe positive, well, let's see. Let's just say it registers positive 65. Going back to Pendleton would register negative 65. That'd be a little weird. So we have a speedometer instead. So the speed equals positive 5/2. Right, let's just check ourselves. Yeah, good. Okay. What about the acceleration? What do we do to find acceleration? Derivative of velocity. Good. So A of t would just equal what? Yeah, derivative of cosine is going to be negative sine times the -5, positive 5 sine t. So A of pi thirds would just equal 5 times sine of pi thirds. What's the sine of pi thirds? Why do you Ah, good. We get square root of 3 over 2. So I end up with 5 radical 3 over 2. Not bad. Yay or nay? That's probably a yay. I think that's not hard. So yeah, it is. So f of x equals the quantity, negative sine x, and 1 minus cosine x squared. So at the outermost level, what kind of a derivative is that one? It's chain rule. But the outermost link in the chain is what? Is it a power? Good. The outermost level, I've got this thing that's being squared. So f prime of x is going to equal 2 times that quantity to the 1. Okay, now if I peel away that outside layer, what have I got? I got a quotient. So I got to multiply this whole thing by the derivative of that quotient, right? That quotient rule, that's the harder one. So what's the quotient rule going to look like? What times the derivative of what is the first term? Okay, good. Bottom times the derivative of the top, right? So I get the quantity 1 minus cosine x. What's the derivative of negative sine x? Negative cosine x. Now what? what goes there? Minus, good. And that's important. There's a tendency, people want to put a plus there because the product rule has plus, but no, it's a minus. So then we flip it, so minus negative sine x. What's the derivative of 1 minus cosine x? Derivative of 1 is 0. Derivative of cosine x is, okay, what is negative sine times that negative 1 is going to be a sine x? All over 1 minus cosine x, yeah, quantity squared. Okay, so what's that give us now? If I multiply straight across, what am I going to get in my denominator? Yeah, good. I get a 1 minus cosine x times a 1 minus cosine x squared. So on the bottom, I'm just getting a 1 minus cosine x quantity cubed. Now on the top, it's going to be a little bit of a mess. I've got my negative 2 sine x, but then I've got some stuff I can do up here, don't I? So if I distribute that negative cosine x, I'm going to get, what, cosine squared x minus cosine x. Good. And then here, if I distribute the negative, well, if I just multiply that out, I'm going to get plus sine squared x, right? Okay, do we see anything we can do in there that helps? Yeah, good, good. There you go. So sine squared x plus cosine squared x, there's our Pythagorean identity, right? That adds to 1. Okay, so that helps. So then I get minus 2 sine x times 1 minus cosine x over 1 minus cosine x cubed, right? Okay, anything else I can do? Good, good, good. Can cancel this out. So I've got a 1 minus cosine x to the 1 there. Can cancel out one of those and give me just a 1 minus cosine x quantity squared on the bottom. That's it, looks like. Nothing else we can do, right? Okay. So now, there's a lot of algebra. That ends up looking quite different from that, doesn't it? There's a lot of simplification there at the end. Let's just check. Yeah. Okay. And that's it. Did it all. How about that? 4 minutes to spare.